Okay, my first time trying this question, I misinterpreted what they're looking for, but I think I have it now. They're looking to build this right cylinder. And the question is, how much work does it take to build it going up? The tower, oh, you're going to assume it's not drawn like this because the tower would roll, right? So that can't be it. Then it takes work to build this object because you have to lift the material against gravity, I guess, is what they're talking about. How much work does it take to build this object? It's got a height of 5 meters and then a radius of 0.8. So to find out how much work is done, we take force times distance that we exert that force over. The force in this situation is the mass times gravity. We need to know the mass of this object. The mass of the object is found by taking the density of the material times the volume of the object. Let's see. So the volume of the entire object depends on how high we've gone, I guess. Right? Because at the very beginning, if you're using this material, there's no volume. And then if you were to take 1 meter high of this type of cylindrical material, then there'd start to be some volume. I think the question is asking us to apply calculus with these infinitesimally small slices right here. So picture slicing this right cylinder in half, and we want to find the volume of one of these infinitely small slices. The volume, it would still be a right cylinder. The cylinder just has an infinitely small height. So the volume would be pi r, which is always 0.8, regardless of where you take that slice, right? Up here, it's 0.8. Over here, the radius is still 0.8. So r is 0.8 squared. The height is infinitesimally small, so we'll use dh, where h stands for the height of this whole thing. That's the volume of one slice. And if we multiply that by the density, I'll do 0.8 squared times the density is 600. That's 384 pi dh is our mass. And then the force for one of those infinitesimally small slices is just that mass times gravity, which is 9.8 meters per second squared. 3,763.2, and then that's with respect to h. So that's for an infinitesimally small slice that we took out of the object that we're building. And so now the calculus part comes in. The work is an integral from a starting to an ending point of our force function. But work is force times distance. So the distance that we have to move this material, it's going to be a total of 5 when we're all said and done, but it depends on, how high we built it at the very beginning, you don't have to move this material very much, so there's not a lot of work being done, right? Because you're at ground level. And then after a while, it starts getting higher and higher. So we need a variable to multiply times force for work. So in the end, what we want to calculate is the integral from 0 to 5, because this thing has a height of 5. And then it is our force at a particular, our force to move that infinitesimally small slice of the volume times the distance we have to move it, which is h. Right, so this slice, maybe that's a height of 4. This slice is a height of 3.5. This height is a slice of 3. So we need that variable h. to finish helping us calculate the work. So if you integrate that with respect to h, then we've got 3,763.2 h squared over 2 from 0 to 5. And then if you plug in 5 squared times 3,763.2 and then divide that by 2, I've got, I dropped pi right here. That's a big mistake on my part. Force, I dropped pi when I wrote it down, so we still need to have a pi on the outside, so this is times pi. So multiply that by pi. We got 147,780. So 147,781 because the instructions asked us to round the nearest integer.